the assistance program. So I wondered if that's
It's
what-
on
yeah. I thought that was kind of weird. Like,
Yeah,
1 o'clock.
oh,
So, okay, we're live, right? Okay. So the homework assignment is due tonight. And I see that there are some homework problems on the board. Didn't we solve some of those problems in previous classes, no?
We only solved 9 on.
We solved 9. So keep in mind that many of the problems in the homework assignment are multiple choice, and you're always going to get the points for them, but you have to figure out how the Lenz's rule works, because you're going to encounter similar situations in the midterm, and the midterm is coming because we're starting chapter 23 today. So let's see, let's solve some of those problems. I don't know if it's worth solving all of them. Probably we can solve some of the problems that are on the homework assignments. Okay. So let's start with problem number 10 from the homework assignment. So the problem is about a solenoid with given size and a current in the solenoid. You have another solenoid, a smaller solenoid, wrapped around the first one. So it has the same cross-sectional area, but only 10 tons, the second solenoid. And in this second solenoid, the circuit is closed with a resistor that for my version is 3.7 ohms. And you open the circuit in the large solenoid. The current there dies in certain time interval. Find the induced current in the small coil. So look, you need to use, in this problem, you need to use several results from previous chapters. So first, the magnetic field inside the large solenoid is easy to find. That magnetic field inside the large solenoid is given by magnetic permeability of air times the number of turns per unit length, which is given for my version, it is 100 turns per unit length. So this is lowercase n, times the current that is flowing in the solenoid. And this is the current for my version is 0.36 amps. So this gives you the magnetic field. And look how the geometry looks like this. Here is the large solenoid. So the magnetic field inside this large solenoid is like this. And we just wrote its value. And around this large solenoid, you have 10 turns like this. And they're connected with the resistor with resistance R like this. So while the current is flowing in the large solenoid, you have this constant magnetic field. But once you turn off the current in the large solenoid, that magnetic field drops. Therefore, in the small solenoid, you're going to have magnetic flux that is changing in time. So the original magnetic flux in the red solenoid is this. Magnetic flux in the red solenoid, call it phi magnetic, let's say, is whatever is the magnetic field multiplied by the area. And we're talking about this cross-sectional area right here, this cross-sectional area, which is given, for my version, it is 2.4 times 10 to the negative 4 square meters, times cosine of the angle between the magnetic field lines and the normal to the area. Well, the normal to the area is this way, the magnetic field lines are in the same direction, so the angle is 0, cosine of 0 is 1. So we're not writing. But this red solenoid has 10 coils, 10 turns. So you have to multiply it by the number of turns in the small red coil. So this is the magnetic field while the current is flowing in the white solenoid, in the large solenoid. And the magnetic flux in the red is this. You turn it off, you turn off the current, the magnetic field, so this is magnetic field initial, magnetic field final becomes 0 because current disappears. In other words, the change of magnetic field, magnetic flux, is the difference of final minus initial magnetic. In other words, it is the number of turns 10. Oh, weird. I didn't mean to write with red chalk, but it happened. And now you can say that the induced voltage in the small solenoid, according to Faraday's law, is the rate of change of magnetic flux in time. A negative sign is present there. So I have a negative sign here because the final is 0, the initial is this. So, and this negative sign with this negative gives you positive. So you get that the induced voltage is AN divided by the time interval delta t, which is also given. So this is the induced voltage in the red solenoid. They are asking what is the average current. This is the average induced voltage. The current, according to Ohm's law, is going to be the induced voltage divided by the resistance, which is, for my version, that resistance is 3.7 ohms. And that's it. In other words, the answer looks like BAN divided by R and divided by the time, where B is this. Capital N is 10. And, well, you just have to calculate the resulting induced current. Yes.
One question I have is for that underneath the resistor that you drew, the equation. Yeah, when you learned it, I thought it was N times the flux equals B times A. So when you move N to the other side, when you divide by it, so I'm just confused why it is on the top.
No, look, this is the total flux. So B times A is going to be the flux through one turn. One turn. B times A is the flux in one turn of the coil. 10 turns are going to have 10 times larger magnetic flux. So, well, we brought some formulas with N times phi or something, but it was in the in the context of transformers, mutual inductance. So use reasoning, and sometimes the formulas are different from other formulas because the meaning is different. Any other remarks, questions? Okay. So again, pay attention to the multiple choice questions. They're conceptual questions. They're very important. They teach you the meaning of what we write as solution of problems like this one. Okay, let's see what is the next problem that is on the board. Okay, problem number 13. Problem number 13. You want to make a solenoid like this one, but you want its inductance to be 1 millihenry. Milli is 10 to the negative 3. For my version of this, the inductor has to have a cross-sectional area that is given and length that is also given. How many turns do you need? So we need a formula that I didn't derive. This is a formula that is probably in the textbook. Let me see if we can derive it easily. Well, so we didn't derive that formula, but I think it is a formula that is in one of the examples in the textbook. That formula comes from the definition for self-inductance. So we said that if you have a single solenoid and you have current flowing through this single solenoid, you're going to, that current is going to generate magnetic field and magnetic flux. And we said that the magnetic flux, total magnetic flux in this solenoid, and total magnetic flux is a number of turns times the flux through a single turn, has to be proportional to the current in the solenoid. And the coefficient of proportionality is what we call inductance. Well, in this expression, so from here, you can say that the inductance is number of turns times magnetic flux that goes through a single turn divided by the current. But look, the magnetic field inside the solenoid has this strength. And it is in this direction. So the magnetic flux is going to be, the magnetic flux through a single turn is going to be equal to the magnetic field, which is this expression, multiplied by the area of this single turn, multiplied by cosine of the angle, but that cosine is again equal to 1, so I'm not going to write it. Divided by the current. And now look, since the current is not given, we have to cancel it. So substitute the magnetic field with its equal. So you're going to get L is equal to N. So instead of magnetic field, I'll write mu naught times number of turns per unit length. times area divided by number of turns times current times area, right? Times current times area divided by current. So current cancels out. And keep in mind that N is equal to the number of turns N, capital N, divided by the length of the solenoid. In other words, the inductance of a solenoid becomes equal to number of turns squared, magnetic permeability times area, and divided by the length of the solenoid. So this is the formula that gives you the inductance of a cylindrical solenoid like this one. And for us, so for us, they want certain value of the inductance. They give the area, they give you the length, you have to figure out N. So you have to solve this expression for N. And it is going to look like this. So when you solve this expression for N, you have N squared is equal to inductance times the length divided by magnetic permeability and cross-sectional area. So this is, and N itself is square root of this expression, so you can, and this should work. And when you get this number, it has, you have to enter integer. So it is unlikely that you're going to get an integer here. So you have to check how to round that integer to the closest, that number to the closest integer. Well, try, yes.
So the lowercase n represents the number of loops in the coil, right?
Lowercase n represents number of turns per unit length, yes. So here you may have, I don't know, you may have 10,000 turns per meter of length.
And then the larger n
Is the number of turns, 10,000.
Oh, they're the same?
So this is total number of turns divided by the length gives you the number of turns per unit length.
Oh, per unit, okay.
Per unit length. But here is a useful formula for inductance of a solenoid. Yeah.
Where you have inductance equals the turns times the magnetic flux over current. How did you get, so then you move to the next where it equals number of turns times magnetic field times A. How did you get the area out of that?
So magnetic flux is defined as a product, magnetic flux through certain area.
A times B.
A times B times cosine of the angle between the magnetic field vector and the normal to the area. The normal to the area.
Okay.
And magnetic, so if the solenoid is like this, magnetic field inside the solenoid is this way. The area is the cross-sectional area of a loop, and the normal to the area is in the same direction. Okay. Other questions? Max? Yeah, I'm okay. Surprised that nobody asked yet for this problem before, but people, okay. So problem number 14. So mutual inductance can be used as a basis for metal detector and so on. Two coils parallel to each other, common axis, AC generator. to the primary coil causes voltage to be induced in the secondary. When someone without metal object walks through, the induced EMF doesn't change. But when a person carrying metal walks through, mutual inductance increases. The change of EMF can be used to trigger alarm. If the mutual increases a factor of 2, find the new value of the induced current. So look, we proved that the induced voltage in the secondary coil, we proved it, and I don't want to prove it again because we have to save time, but we proved that the induced voltage in the secondary coil is equal to the coefficient of mutual inductance, well, there is a minus sign, times the rate of change of current in the primary coil. Right. So they say that here you have certain induced voltage when there is no metal around. If you increase the mutual inductance by a factor of 2, the voltage also has to increase by a factor of 2. Right? That's it. Because the current in the primary is what it is fixed number. It is what the generator gives you. So the secondary prime is equal to 2 times M. This is the mutual inductance times the same rate of change as the primary coil, which is equal to 2 times the voltage, the original voltage. Right? So this problem is put there just to tell you how metal detectors work. So this is problem 14. Remarks and questions here? Yeah.
What's the value of that?
Well, you don't need it. They're just telling you that you're doubling it when metal is placed around the metal detector. So M is some number of millihenries or henries. Some coefficient of mutual inductance, depending upon how close the 2 coils are, what is the orientation of those coils, what is the size of each coil. So it is geometry dependent number. Okay, other questions and remarks? If not, let's do problem number 15. Insect zappers, blue light, high voltage. So they say that one device uses AC voltage of this, obtained by a 110 volt outlet via transformer. If the primary is 18 turns, how many turns are in the secondary? Well, the formula for voltage in a transformer looks like this. So voltage in the secondary divided by the voltage in the primary is equal to the number of turns in the secondary divided by number of turns in the primary. So they practically tell you that voltage in the primary is 110, right? At least for my version. They tell you that voltage in the secondary is, for my version, is 4,230. volts. And the primary, the number of turns in the primary is for my version 18. So solve this expression for the number of turns in the secondary. So you have the number of turns in the secondary is equal to the number of turns in the primary times Vs divided by V. So do this multiplication division, and you have to get the right answer.
Would this be a step down transformer?
It's a step up. You go from 110 to 4,200 and something. So this means that, and you're going to see, this is 18, this is going to come to almost 700. So when the secondary coil has larger number of turns, you have higher voltage in the secondary circuit, and you have step up.
So if we had started with 110 and then the secondary was like 11, that would be a step down
Yeah.
transformer.
Yes, that would be step down transformer, and well, but it's not going to work.
Right.
For
I don't want to take more time on that multiple choice question, but I am really lost on number 11 on why it is what it is. Go over number 11 really quick.
what is number 11? Oh. Yes, so this is a good question. And look, yes, this is a good question, and please pay attention to those multiple choice. There, I have spent substantial amount of time to select multiple choice questions that are meaningful. And this one is one of the tricky ones. But you're going to encounter something similar on the midterm. So you have a wire with current, and after that you have a single loop of wire that is falling. Yeah, well, I don't have my props, but here is a single loop of wire. Well, it's not very close. You can imagine the single ring that is falling from position 1 to position 2. Determine the direction of the induced current as the loop moves. So while the loop is in position 1 and moving downward, look what happens. Here is the current. Here is the current flowing this way. The magnetic field created by this current from the second right-hand rule is going to be out of the board on this side and into the board on this side, right? Because the right-hand rule this way. So this is the direction of the magnetic field. And that magnetic field is stronger when you're closer to the current and weaker when you're farther from the current. If you recall, that magnetic field in magnitude is mu naught times I divided by 2 pi, the distance r from the current. So when the coil is here and coming down, it is getting into magnetic field that is out of the board and increases because you get closer to the source. It increases out of the board. You want to generate, according to Lenz's law, you want to generate current that induces magnetic field in direction to prevent, to fight this change, this increase of flux out. In other words, you want to have induced magnetic field in. And induced magnetic field in is going to happen according again to the right-hand rule, but now applied to the ring, is going to be if the current here is flowing this way. So this is the direction of the induced current. And this induced current is going to create magnetic field that is into the board to try to prevent the increase of out of the board flux that goes through this ring. So it is multiple, it really needs not only working with your mind, but also working with your right hand rule. Right hand. So after that, in the second position, when the ring is here, but again moving this way, the magnetic flux that goes through the ring now is going to be out of into the board, right? Into the board here, but getting weaker because you're going farther away from the source, getting weaker. So you want to compensate for this getting weaker by generating additional magnetic field into the board. So you generate additional magnetic field into the board if the current again is going in clockwise direction. So it generates here additional to compensate for the reduction of strength of flux as the ring falls or goes farther away from the source. So, well, this it is a lot of talking, but it requires you to sit down, see the lenses rule again, a second time, a third time, talk with me, talk with tutors, talk with friends, and eventually you're going to feel quite comfortable with this. Yeah.
Sorry, I don't get it as well as I should get either, but so this is the right hand rule. And you're saying on that top one, current is going into the board or coming out of the board?
The current is going clockwise.
Sorry, the magnetic
The
field
induced magnetic field has to go into the board.
into the board. And so if you're using right hand rule number 2, are you using it on that current that's going straight across?
I'm using the right hand rule twice. The first time I used the right hand rule to determine the magnetic field around the current.
Okay.
The current that is flowing, not the induced current, around the straight current.
And that would show the current coming straight out of the board.
Out of the board, magnetic field on this side, into the board on this side, right? Because you have to, here is the current flowing in this straight piece of wire, here direction of current, you have into the board on this side, out of the board on this side, right? This is the magnetic field around the straight piece of wire. And after that, Lenz's rule says that the magnetic flux of this field, if it is changing, you induce current in this ring to try to prevent the change of flux that goes through this area. So the flux that goes through the area of this ring is out of the board and increasing because you're getting closer to the source. So you want to prevent this increase by generating opposite direction magnetic field. So this magnetic field has to be into the board, and this is induced magnetic field, right? It is due to this induced current, not to any other current. It is a multi-step process. It requires really spending time.
So what makes it clockwise instead of?
Well, the right-hand rule says that in order to have induced magnetic field into the board, you better the right-hand rule again, but now right-hand rule around this ring. Again, there are multiple questions of this type on the homework assignment. You have to think about each of those multiple questions. This homework assignment and the previous one also. The previous chapter 21. Okay, some people are really bored with this. Let's start something more. Let's start something more exciting. What is more exciting? RCL circuits or a quiz on the screen? What do you prefer?
On the screen.
On the new chapter, chapter 23?
No, I'd rather go instead of 14 quiz.
I thought you were talking about quiz on this.
No, but we're not talking about, we want excitement. And what is more exciting than a question that you don't know how to answer? Right, that's, okay, let's. Okay, so chapter 23 is the basis of electronics practice. The chapter discusses the behavior of RCL circuits, circuits that contain resistor, capacitor, and inductor. And we're going to start the study of RCL circuits by studying the behavior of circuits that contain only one of those three circuit elements. Let's start with a circuit that contains only a resistor with resistance R connected to AC voltage supply. And voltage supplies, the voltage changes as a sine function, right? It changes as amplitude V naught times sine of 2 pi f t. T is the time, f is the frequency. So let's start studying this simple circuit, which doesn't hide any surprises, but we're going to introduce the framework to study circuits that are a little bit more complicated. So first, let's show how the voltage changes as a function of time. So voltage as a function of time, of course, we say that it is a sine function. A sine function looks like this. Yes. So this is the time axis here. So here the amplitude of the voltage is right here. This number is the amplitude. Here is again the amplitude, but with negative direction. This is the period of oscillation, which means that the time interval from here to here for the voltage, like the voltage on the socket here, is 1/60th of a second because you have 60 hertz frequency. How does the current change here? Well, Ohm's law tells you how the current changes in this circuit. The current, the voltage, and the current change in sync. And they differ by a factor of resistance. In other words, the amplitude of the current is equal to the amplitude of the voltage divided by resistance. And on the diagram, if this is current, well, the voltage and the current change together, so you have exactly the same type of function. Of course, the amplitude now is some number that you can calculate, right? And also the RMS value of the voltage and the current are again connected with the same Ohm's law. The next diagram here is to see the power consumption in this circuit. And if you recall, power consumption can be calculated as a product of the voltage times current. So this is, if you take instantaneous value of the voltage times the value of the current at the same instant, multiply them, you have the power consumption at that instant. The average power consumption, of course, is going to be product of RMS value of voltage times RMS value of current. And look, the power consumption is going to look like this. So in the first half of the interval here, the first half of the period, both voltage and current are positive. So the product of two positive numbers is going to be a positive number. So the product of those two is going to look like this. So this is the power. At the next half of the period, the voltage is negative, but the current is also negative. The product of two negative numbers is another positive number. So the power consumed is again going to be the same positive power, and so on. So the average power consumption, of course, is going to be some positive number. Now, look, it doesn't matter what the frequency of the signal that comes from the generator is. The resistance is always going to be the same. Whatever number of ohms, let's say 50 ohms or whatever is your resistor connected here. In other words, the resistance as a function of frequency is going to be a constant number equal to the value of the resistance of the resistor connected to your circuit. And now let's introduce a little bit of another way of looking at this diagram. Let's represent the value of the voltage with the so-called phasor. So look, I'm just going to have two perpendicular lines, no directions, no zero. And I'm going to think about the voltage as a vector, like this. The voltage provided by the generator as a vector with length equal to the amplitude of the voltage, this amplitude, with this length. And at an angle right here, this angle equal to the value of the angle under the sign at certain moment of time. So at moment of time 2 pi, at moment of time t, this angle is going to be 2 pi ft. At the next moment of time, this phasor is going to rotate. As the time increases, this is going to rotate. So it is going to circle like this with frequency f. Right? At the next moment of time, it is going to be here and so on. The instantaneous value of the voltage at moment of time t is going to be given with this length, because this is exactly sine of V naught. V naught times sine, here it is V naught times sine, is exactly this length. So this is the value of the voltage at moment of time t, this length. In other words, at moment of time t, here is the voltage at moment of time t, here, this voltage. So this phasor is constantly spinning, and at any moment of time, you can figure out what is the value of the voltage provided by the generator, just as looking at the sine of this angle times V naught times the hypotenuse. So this is the phasor notations and the phasor way of thinking. similar to vectors, but with some twists. Now, the current is represented with a similar phasor. So the current is right here. So here is the phasor representing the current, right on top of the phasor representing the voltage. But it is in this case, it is smaller by a factor of R, factor of resistance. So the instantaneous value of the current again is this length. Okay. Well, we have 4 more minutes. Let's do the same type of reasoning for a different circuit. A circuit now that contains a capacitor with capacitance C connected again to an AC power supply with voltage amplitude P naught times sine again of 2 pi ft, exactly the same generator. And let's follow the same procedure. The voltage that is given by the generator is a sine function. There is no any, right? This is what it should be. However, look what happens with the current that is flowing in the circuit. Well, when the time is shortly after moment of time 0, you have a little bit of voltage, right? The voltage is small, but let's say positive voltage. This small voltage is going to drive easily electrons or charges in general. It is easily going to drive them because there is nothing to stop those charges. And those charges, let's say, are going to come here and start piling up on this plate of the capacitor. Well, at the next moment of time, the voltage is higher, but those charges have harder time making it to the capacitor because you already have positive charges piled up here and they're going to repel the newcomers. They don't want newcomers to come close to them. So even though you increase the voltage, the charges don't move so easily, so the current doesn't increase as you expect. Well, when you reach maximum voltage, you already have certain charge on the capacitor, and after that you start reducing the voltage. Even though the generator is pushing charges in this direction, in reality, no charges can flow in this direction anymore. But the charges that already have been piled up here, you cannot even keep them from coming in opposite direction. So look what happens. The current in this case, once you solve the equations, you can convince yourself that the current behaves the following way. Initially, the current is very strong, even though the voltage that drives it is practically zero, small. The current is very strong because there is nothing to stop, nothing to repel those charges from moving to the plates of the capacitor. But as the time goes up, the current actually drops, even though you push harder with the voltage. And the current actually drops because you just cannot overcome the repulsive Coulomb forces of the charges that already, from the charges that are already on the plates of the capacitor. So you have, instead of increase of the current, you have decrease. After that, you have maximum amount of charge on the plates of the capacitor. And after that, even though you keep pushing, you're not pushing strong enough. And the charges that have been piled up, they start coming back. And the current actually, even though you're pushing in one direction, the current is flowing in opposite direction. So you have this situation. And after that, the same type of reasoning, you end up with a function of the current as a function of time, like this. Like this. In other words, this function is again like a sine function, but if you look at the function representing the voltage, it is like you start from here. We say that the current is leading the voltage by this quarter of a period, by 90 degrees, this quarter of a period. So the current is leading voltage by 90 degree phase. And well, in the remaining time, we have to figure out how the power is consumed. And look, in the quarter of the period right here, both voltage and current are positive, so you have positive power consumed. But in the next quarter, the second quarter, you have positive voltage but negative current. The product is a negative number. After that, you have both voltage negative and current negative. So the result is a positive part. So half of the time, the power consumption is a positive, half of the time, negative power consumption. Negative power consumption means that the capacitor is giving back energy to the generator. So half of the time, the capacitor is drawing energy from generator. The other half of the time, it is giving that energy back to the generator. And the average power consumed is 0. And on Friday, we have to see how the phasor diagram looks for a capacitor and also for the other interesting circuit. So we're going to continue